this? All right, so let's talk about the call stack and recursion. First, we'll start with the call stack. So what is the call stack? It's something, a term that some of you guys might have heard about, but maybe unclear. So let's maybe demystify it a little bit. The call stack is, what is it? Let's start with, what is a stack in the real world? Does someone want to just try to describe what a, when you hear the word stack, can someone just describe it in like layman's terms?
So, a pile of stuff.
A pile of stuff. Yep, that is a good way to describe it. Again, we deal with stacks like stacks kind of in real life. Think about where you stack maybe some Pringles chips together on top of each other. I don't know, you have a stack of papers on your desk. So I think hopefully many of us or all of us are kind of understand what a stack is. It's a vertical pile of objects, usually one on top of the other. Usually like a stack of plates, a good way to visualize it. We talked about before where they'll go bottom up, and you'll kind of pick them off from top down. So what is a stack in the programming world? Again, a stack is a particular type of data structure. We've talked about lists and dictionaries heavily because we use them a lot. Again, stack isn't just another type of data structure that we may encounter, not likely too much in our use case, but again, it's definitely good to know about. So it's a data structure that stores object in ordered manner. So just know that some data structures have order to them. Other data structures do not, but a stack does have order. Provides a single insertion and retrieval point. So when we're talking about insertion and retrieval, we go back to our plates example. When we're inserting a new plate or basically adding a new plate to our stack, we always have one position we can insert in, and that's at the very top. Likewise, we only have one retrieval spot, and that's from the top, right? Again, we're not trying to get too crazy about this. Like, sure, as humans, we can kind of lift half the plates of stacks and take like one from the middle. That's not what we're kind of envisioning here. Just kind of understand that there's one retrieval and insertion point, and that is at the top for, I guess, a physical plate of state, physical stack of plates. All right, so when we're inserting, we usually call that a push, and when we're retrieving, we usually call that a pop. We use these terms with lists, so very similar concepts there. As we kind of introduced last week, stacks are LIFO. When we say LIFO, that's last in, so that's the LI, and then first out. So the last item that you've added to the stack is going to be the first item that you get back out of the stack if you retrieve anything. Again, same plate example. The last plate you put is going to be on top. So the first plate that anyone takes is going to be from the top. So one great example is your web browser history. So again, we deal with stacks in the programming world also, and we might not even know it. So when we have a browser open, if I go to a few sites, let's go to ESPN. Okay, so that ESPN is being put on the bottom of my stack. That's the first thing. Sorry, it's being added to my stack. So ESPN is there. Let's say I go to CNN next. Now we're putting CNN on top of that stack. So we have ESPN and then CNN. Let's go to one more site. Someone have a cool site that's definitely appropriate for us to check here? Anyone want to rep a unique site that we might not know of? Someone's got to have something.
eBaum's World? I'm older than everybody else, I think.
Okay, I have heard of that. I assume that's safe for work. eBaum's. I'm not even sure how to spell it.
Some of it.
Okay, we'll maybe go to Stumble Upon. So this is a cool site, stumbledupon.com. Then just actually find you a random site. So if I go Stumble Upon, it will just recommend a random site. That's probably not where I want to go. Maybe it doesn't exist anymore. Let's just keep it simple. Let's just go to Rotten Tomatoes, tomatoes.com. All right, cool. So we went to ESPN, that was put on our stack. Then we went to CNN, that was put on our stack. And then now we've gone to Rotten Tomatoes, moving rating site. I'm not going to enable ads. But yeah, all right, so that's what we did. But notice our web history is a stack. So if I long press this, notice we get ESPN, CNN, and then Rotten. So at the bottom, we have ESPN. Then we have CNN on top of it, and then Rotten Tomatoes on the very top. If I want to retrieve the most recent item that was in my history, I hit back and notice it goes to CNN. So that was pulled off the history stack. So I guess Rotten Tomatoes wasn't on the history stack since we're still there. But yeah, I went back and it pulls out CNN first. If I keep going back, I get ESPN because that was the next item that was on the stack, right? So again, we deal with stacks every day, even if we didn't know it. So web browser is a great example of a stack that's been implemented. Right, so it's a highlight of why stacks can be useful for our purposes. All right, so hopefully you guys understand a stack data structure. Pretty easy, especially since we deal with stacks in the physical world. All right, let's actually talk about the call stack. So what is the call stack in an application? As you might expect, it's an ordered collection, but of execution context. So instead of plates, we have execution contexts, but they're still being put onto a stack in the virtual sense. So also known as the execution stack, each line of code gets pushed to the call stack one at a time, and then it gets executed. Once a line of code is completed, it gets pulled off the call stack. So it gets removed from that virtual stack that's being created. The key thing is function calls only complete once the return line is executed. So functions can call other functions, and that's going to basically create your stack vertically. So if I have a function A and that calls function B from within it, function A doesn't return right away. It's calling function B. So we're going to get into the function B execution context. That's going to be added to the stack while function A is still kind of executing, right? Because function B is a part of function A. So again, these stacks can get really high. There's something called a stack overflow that you might have run into. And that just basically means that your computer ran out of stack memory. And that just says, yeah, we're not going to continue this. We don't have enough memory for this. But yes, when you get a stack overflow, that just means your call stack has been overwhelmed. You've exhausted all the available memory for the call stack, and it's going to quit. Usually speaking, I assume Macs work the same as Windows, but yeah, your computer is going to allot a certain amount of memory for each application that's running. So I have, a web browser running, I have Zoom running, I have Slack running. All those applications have a set amount of call stack or memory available to them. So, if for whatever reason I'm running my own program and that has a stack overflow, that's not going to take down my entire computer because it's not exhausting all the memory of my computer, just the memory that was allotted to it. Okay, let's actually look at an example because, again, talking about code and seeing code definitely different. So I'm going to grab it off our curriculum page and let's add it to our code here. So let's call it call stack.py. Okay, so pretty simple application here, if I could even call it that. But what's going on here? So I have three functions. I have a function called first, function called second, function called third. I am invoking the first function. So that is my entry point into, I guess, these functions. So I call first. First is going to execute. It's going to execute all this code. Notice that I actually call my second function within my first one. So that's actually going to get into this logic from this line of code, right? That's kind of just how functions work. If you want to imagine it, hopefully you guys understand functions, but I could just copy and paste the code here. It'll do the same thing, but obviously that's redundant code. That's the whole purpose of creating functions. So I'm going to call second. Same thing going on in second, we call third. So the third function is going to go. We are printing out some informative message to kind of keep track of what's going on. So when we actually start our function, we're going to push that to our call stack. So just to kind of simulate adding it to the virtual call stack where function first gets added to the call stack. And then when we get into second, function second will be pushed onto it. When we are done with our execution, we'll pop it off and then return. All right, so hopefully that kind of makes sense. Nothing exciting going on here. I could run this program. You guys won't be wowed by it, but if I do Python call stack. So this is what our output should be. So notice the order of everything. So this is kind of in reverse. Again, stacks, we imagine going up vertically, but this is just executing downwards. Basically, the first thing that happens is that we push the first function to the call stack because that's the first thing we get into. Then we push the second one, but notice we haven't exited our first function yet. We're still, that execution context still exists. So we push the second function because we called it. Then we also push the third function. The third function calls hello world. So it's not going to create another execution context. We're not going to keep going up into another function. So this is where we print out hello world. And then function third has completed its task. So we're going to exit this execution context via this return. So now that this function is dying, we're going to pop it off the call stack because that's done. Everything that line of code needed to do is completed. So we pop third, then we pop second, and then we pop first. So notice that goes in reverse order, right? Because first is the last function to die because it's actually calling second, which in turn calls third. So when we complete this line of code, the last thing that will happen is we'll remove first from the execution context. All right, so that's all what a call stack is. Just kind of keeping track of what's actually running within your application. Let's kind of just visualize this again, just give some context here. So this is the coding example we had. And then we have just, output and the call stack. So whenever your application is running, there's something called the global execution context. Again, not going to really talk too much about that. Just know there's something running there. Actually, I'm not even sure that's true for Python. I know that's true for JavaScript, but we'll just play along with it. So let's get to our first line of code. So again, we're not executing all these lines of code. This is logic within a function. So our first actual application line is first. That is the first execution point. So we run first, we're going to get into this function. We will pop it to the call stack. Then we actually get into our function. And so this print is actually another function, right? We're actually calling a function of print that takes in an input of a string. So we actually pop the print function to our call stack, but the print simply takes in an input and then outputs it. So that's a pretty trivial operation. So notice that print completes and actually push it or add something to the console or the output here. All right, so when we finish that line, we get the second, pop that, or sorry, push that to the call stack. And then we actually get into that function. Again, it's not nothing too complicated going on here, but notice we add the print statement because that's still a function that completes. So we pop that off. Then we get into the third, push that to the call stack. So now notice our call stack just growing. So again, this is a very trivial application, but we're already 4 or 5 levels deep into the call stack. So again, your call stack can definitely grow a lot with large applications. That is something that might need to be managed depending on what you're doing, but for the most part, don't need to worry about that. Obviously, avoid infinite loops. So we print out, push third, get to hello world. That gets added up here. Again, you guys kind of get it. So I'm gonna expedite this. Now that we've completed third, so we're going to pop it off by printing pop. We get to the return. The return will remove the third function here because the third function has completed everything it was going to do. So when we return, notice it gets pulled off. Same thing happens with second. When we get to the return statement for second, that executes and it's going to pull return or the second method off the call stack. And we'll do that for first also. All right, so just kind of understand how your application works. Behind the scenes, we have a stack that your computer manages. This is nothing that you need to manage yourself as a developer. Again, you're just writing code and just understand that your computer is managing those execution contexts in some manner. What questions do you guys have about this example here or anything about the call stack? Okay, hopefully all of that made sense. All right, let's complete our application and we're done. All right, so that was just a brief introduction to the call stack. The reason we introduced the call stack is because our main feature today is recursion. Well, what is recursion? Well, recursion is something that employs recursion. So we got kind of a recursive definition here, right? We don't really know what recursion is because it relies on itself. That's kind of just a small wordplay because that is what recursion actually is. It's something that refers to itself. All right, so something that references itself, part of its definition. That's definitely a better definition than my first one, right? This doesn't really help us. I don't know if you guys know about this. This is kind of just like nerd humor, but our friends at Google, I don't know if you ever tried this. Has anyone tried Googling recursion? So again, check my spelling. I've spelled it correctly. But notice when you enter recursion, it asks you, did you actually mean recursion? So if you click on it, when you make a typo, it corrects you. Click on recursion. Notice it keeps correcting you because you're kind of recursively just going through the same motions here. So again, like a little small Easter egg, I think in the Google search engine. There's a few other ones. I don't remember offhand. There's a few of them you can find. So have fun with that when you have some Googling time. But recursion, and something that references itself as part of its definition. All right. So what is recursion within the programming world? So it's a process involving breaking a bigger problem down to smaller versions of itself. So that's when you want to use recursion. But the idea of a recursive function is basically just a function that calls itself at some point. So if you have, a function like first, if I called first again, let's say I called return, I don't have to return it, but I could call first again. This is in second. If I added first here, now I have a function that calls itself. Obviously, the way I have it right now, this is going to be an infinite loop because first is going to do all this stuff, and then it's going to call first again, which is going to do all this stuff again. So it's going to go over and over and over. It's never going to get to this return. So if I actually ran this, let's actually run this. Notice it kept going. So if you guys see it, it just kept going and going and going. Eventually, we hit our limit. In this case, it looks like around like 1,000. It says, yeah, I'm giving up. Maximum recursion depth exceeded while calling a Python object. So Python has limitations on, I guess, how many times you can call the same function. But yeah, again, if Python didn't protect us, eventually our operating system would cut us off. Again, they're not going to give us free reign or free resources because we don't want to take down our entire system. But yeah, again, if you get into an infinite loop, you can hit Control-C to abort it. In this case, this ran pretty quickly, so I didn't need to abort. But just know that you can abort it via Control-C. All right, but yeah, this is still recursion, even though it's an infinite loop. It's still a valid case of recursion. It's not proper coding, but it is recursion. All right, so again, that's all what recursion is. Let's look at an example. So the Fibonacci algorithm. What are the main parts of a recursive function? Sorry, I guess example to come, sorry. So there are two main parts that you should implement for a recursive function. One is the base case. This is your special condition where your call stack will stop growing. It's going to hit that point and basically start building back down or tearing down. So this special case, you should always have a base case. Without a proper base case, you'll get a stack overflow, or also known as an infinite loop. All right, so again, always make sure you have a proper base case that will eventually be hit. The recursive case is basically the common case or the general condition where you call the function again. So again, the whole idea of recursion is kind of using the same logic over and over, referring to the same function, to the same thing. And this is very useful for when you're taking a bigger problem and breaking it down into smaller sections. All right, so just know recursive case is the common case, base case is your special ending case. You could have more than one base case. I want to make that clear. You don't necessarily need one base case, but you need at least one base case so that your call stack doesn't keep building up and up and up, calling the same function again and again and again. So iteration, this is something we're familiar with. Whenever you hear the term iteration, just think loops, for loops or while loops. That is iteration at work. So iteration is the process of doing something repetitive, using a loop. As we talk about for loops or while loops, you guys have been doing this, so you guys are probably pros at it. We should be iteration masters at this point. Important note here, all iterative solutions can be done recursively, and vice versa. All recursive solutions can be done iteratively. Just know that. But again, so the question is, when do we use which? Like, when do we iterate? When should we use recursion? My rule of thumb, this is my opinion, usually speaking, 95% of the time, you should be using iteration. Even though you can use recursion, in my opinion, iteration is going to be simpler to implement and easier to understand. But there are a few cases where recursion makes more sense. And that's obviously why we're talking about it. If it never made sense, then we probably would just avoid the topic entirely. But again, if you're trying to debate like, hey, I could solve this iteratively or recursively, which one should I do? More times than not, it's going to be iterative is the way you should go, just for your sanity and just your code sanity. Let's take a look at the Fibonacci sequence solved using iteration. So in this case, we create three variables, one called F, A, and B, initialize those to 0, 0, 1. Sorry, I just want to back up. Everyone clear what the Fibonacci algorithm is? It's basically the sequence, generating the sequence. Just want to make sure everyone's on the same page. Sequence. Wish they had it. All right, let's go here. Wikipedia is probably better. But yeah, the Fibonacci sequence is the sequence of numbers with a certain pattern. And that pattern is basically the next number, so let's look at this number, is generated by summing up the previous two entries. So in this case, 3 is a sum of 1 and 2. 5 is a sum of 2 and 3. So it's exactly the two previous values. The first two values are special, as in they're just starting off at 0 and 1. But then the third and every value ahead of that can be computed from knowing the previous two values. I guess the catch here is I can't automatically just know how to get, what is this? 1, 2, 3, 4, 5, 6, 7, 8. The ninth value. There's no magic way to compute the ninth value directly. We actually had to do it in steps, because this depends on these two values, but these two values depend, like this value depends on these two, and this value depends on these two, right? You can kind of see how it's kind of building up. So I can't just say, hey, what's the ninth Fibonacci number? I actually have to know what all these values are before it to compute that value. So that's what I've coded up. We got here. This is the Fibonacci sequence generated there. So the way we do it is basically add two numbers. In this case, A and B are our starting special values, 0 and 1. The next value is going to be F. So F is the previous two values, which are A and B. Then we need to update A and B for the next iteration, if there's going to be one. So in this case, A will take the value of B. B will take on the new current value, so that when we do the next value will be the current value plus the value 2 steps before it. Kind of a mouthful to say, hopefully the concept kind of makes sense. So looking at this coded up solution, iteratively, sorry, I can't say that word, iteratively, we're using a for loop and basically going up to a certain number and then going to repeat this process until we are satisfied with our for loop execution, then we return that final value. So this works. This is a 100% working solution. Honestly speaking, this isn't too complicated because this algorithm isn't super crazy. But again, simple example, but hopefully you guys can extend it, just understanding that there can be more complicated solutions. But let's take a look at the recursive solution here. This is a recursive solution. You'll notice a few things, but one thing you'll notice is that we're calling the function again as part of the definition. So in this case, we are calling the function twice with different values, right? So we take an n value and then we pass it n-1, n-2, and kind of call it again and do that again. So maybe visually you can understand maybe how many times are we calling this or how the operation is being broken down. But in this case, this return value is our general case. So sorry, there we go. That is our recursive case, right? Because that is the point where we're actually calling our function again. So this return statement right here, this is our recursive case. Our base case is right here. So in this base case, we check for our special condition, in this case, when n equals less than 2. That is when we stop calling this function again. So notice our return here, we're no longer going to add on to our call stack. We're going to tear down, because this return is going to exit this call. And then previously we're going to return, sorry, it's kind of confusing to explain. We're going to return whatever values returned here. So this return is going to break down the previous call stack. It's going to just keep tearing down now, because all we're going to do is return whatever the previous, the call stack on top of is returned. So it's going to be, okay, I'm returning you this. All right, that call stack is going to say, all right, I'm going to return my call stack underneath me, or the execution context beneath me, whatever I'm returning. It's going to tear down really quickly. Again, you don't always have to return your recursive call. In this case, that's how the algorithm works. But you can call Fibonacci recursive, store that value, do something else if you need to, and then return something else. All right, so you're not always going to see the recursive call as part of the return. But the things we want to highlight here, just kind of bouncing back and forth. So this is iteratively, and this is recursively. Notice that the code is much more concise, right? We're down to like basically 2 or 3 lines of code. This I would say is more elegant, and I would say, personally speaking, and this might be subjective, I think this makes me understand what the Fibonacci algorithm is doing than the previous example. And this, it's clear to me that, okay, the current value depends on the past two values, n-1 and n-2. Looking at the iterative solution, honestly speaking, if I never heard of the Fibonacci algorithm and I was looking at this code, I wouldn't be able to snap my fingers and say, hey, I understand the Fibonacci algorithm, right? Again, looking at this, I could probably piece it together, kind of stepping through it, but just reading this code, it's not clear exactly what the Fibonacci algorithm is. Maybe you would agree, maybe you wouldn't. Again, kind of subjective, but I think this makes much more sense in terms of conveying what we're actually doing for this computation. So that kind of gets into the advantages of using recursion. So generally, not all the time, but generally speaking, it will reduce the amount of code that you are writing and maintaining. And that can be a benefit because just the sheer nature of it, the less code you write, not always, but the less code you write, the less bugs that can creep in there, right? One line of code is generally going to have less bugs than an application that has 1,000 lines of code. Again, not always, but generally speaking, there's some correlation there. Keyword here is may. It may lead to a more intuitive solution. In the case of Fibonacci, I think that is true, but that is not always true. Sometimes implementing recursion makes your code much harder to understand. And that is a negative, actually, of recursion, which I'll be on the next slide. It may reduce time complexity of your algorithm. Not always, depends what you're trying to solve. In this case, oops, I keep going back to the wrong thing. In this case, time complexity has not been changed at all. We're doing the same number of executions. In fact, recursion will actually take longer because there's a minimal overhead of adding a new call stack and tearing it down. So that could slow down your execution there. But again, depending on the algorithm you're trying to tackle, it may reduce time complexity. And we will see an example of this, if not today, probably on Wednesday, when we actually talk about time complexity more in detail. Note that recursion definitely has its place in the programming world. So as I said, most of the time, iteration is the way to go, just using for loops. But when you're talking about branching algorithms, divide and conquer, backtracking algorithms, these are very popular use cases for recursion. One example, think about searching your file system. I wish I had a great example, but just imagine having multiple folders. So let's actually try to create this here. Let me create a folder. It's called A. Then call a folder B, folder C. You guys know how file systems are organized, right? And within this, might have a file called A or 1, and then again, not the best example. Hope you guys can live with my examples here. Let's create a file called 3, a file called 4, and then maybe another folder. Let's call it Apple, and then 11. I'm not sure even where I'm going with this, but we'll reach some point that makes sense, hopefully. Banana, and maybe some more folders. Another B fruit. Is there another B fruit? Someone help me out, please.
Apple.
Apple?
Or a pineapple.
Pineapple, grapefruit. If you guys have never had a pineapple, well, I wouldn't blame you because I don't think it exists. All right, pineapple.
Berry.
Okay, so again, this is our file system. Let's say we need to search for something. Let's say we're looking for a particular value, right? Let's say we're looking for the value of 4. I want to find a folder or a file called 4. So what your operating system is going to do is actually going to search recursively in all these folders and then recursively go down to nested folders. That is the fastest way to do this. But you don't have to. You could do this iteratively. So what I mean by that is if you're coding this up, you could first find your first item, which is folder A, go into its children, and then find what children exist. In this case, we find 2 children, so we go to the first one, check Apple, and since this is a folder, we need to check its children. So then we're going to go into it, check 11. Nope, that's not what we're looking for because we're looking for 4. So okay, we exhausted all the children for Apple. Now we go back up. We're done with this child. We go to the next child. Okay, this is not a folder. We check it. Nope, not what we're looking for. Then we're just going kind of in order. So we go to B. We check B. Okay, didn't find what we're looking for. Anything in here? Nope, nothing there. All right, this child doesn't match. Again, you guys understand we're just going kind of in order here. Eventually, we get down to D, and then we search its child. And yep, that's what we're looking for. We're looking for file 4. That definitely does work, but is not the most optimal solution. The reason is because we have to go basically through each child in order. The better way to do it is kind of branching top down. So the other way to do it would be, let's check all the children here, which is A, B, and C. At the same kind of time, we're going to check all of children A. Then we're going to search all of children B, all of children C, and then all of children D, kind of in order. So A children, B children, C children, D children. If we don't find it, then we're going to go to the next level. We're searching the grandchildren of A, grandchildren of B, grandchildren of whatever else. This is what's known as breadth first search versus depth first search. But sorry, I might be kind of breaking this. But anyway, the idea is you kind of just break it down to smaller problems where you search children kind of in the same call. So again, file system search, recursion is the way it's done. You could do that iteratively, but sorry, let me amend what I just said. It might not necessarily change the way you're searching, but it's going to change the way your algorithm looks. So file system recursive is the way to go, rather than having a bunch of if statements to control your flow. Let's talk about disadvantages of using recursion. As I mentioned earlier, it requires more memory because you're going to be keeping track of extra function calls and extra execution contexts. Each execution context like has local variables and you need to keep track of some data. So that again has some memory overhead, which can be a huge negative of recursion, especially if your call stack gets really large. Generally involves more time complexity. Again, depends on your use case. Usually it's going to be equal to your iterative solution because again, it's just another way to do iteration with functions. So in functional programming, recursion is kind of your go-to. Can run into stack overflows, which you talked about, can crash your application. So if you don't have a proper base case, recursion is going to get you more into trouble. I mean, you'll still have an infinite loop with for loops, but I would say that's less worse. All right, so let's just, again, key takeaways. Again, as I mentioned, not too much to know here. Know what a stack data structure is. Again, this is more for your interviews. When you get to interviews, hopefully they don't ask you because I don't think it's a great question, but they might ask you, hey, what's the difference between a stack data structure and a queue data structure? That's probably a popular question. So we talked about queues in passing, but a stack is LIFO, last in, first out. A queue is FIFO or FIFO, which is first in, first out. So stacks versus queues is, again, a popular interview question. I don't know how popular they are, but there is, again, kind of a buzzy question to ask. But outside of that, understand what the call stack is. Again, this applies to basically every application you're writing. Every application that's running on your computer right now employs the call stack. This is not something specific to Python or just JavaScript. It's every programming language you deal with works with the call stack. Last takeaway, just know what recursion is, how to use it, and when to use it. So again, most of the time, you're not going to have to use recursion. I think for challenges tonight, we're going to force you to use them just to get that practice, obviously. But again, it comes down to understanding the benefit of recursion and why you might want to use it. Again, elegant code can reduce the number of lines of code you had, right? Can make your algorithm more intuitive or more understandable. And depending on the algorithm, can be more beneficial. All right, so that was just our intro to recursion. Again, something you'll get practice with, just another way to solve problems. Again, that's the tools we're giving you. We're adding to your toolkit so that you're aware that this exists and that you could use them, in your future when you might be like, okay, this smells like a case where I'd want to use recursion just because I see the components for it. Okay, any questions about call stack, stack data structure, recursion? All kind of makes sense. Okay, just know recursion is another way to solve a problem. Usually you can always solve it with a for loop, so don't have to use recursion, but want to get practice with today's challenges. So let me stop the recording here.